So dear students, in the last period we have studied about the factors affecting the acid strength. So there are various factors that affects our acid strength, especially when we want to study them in a particular group or in a particular period. But we need to know why should some acid be stronger than others, and what are those factors that determine whether the acid is weak or strong, whether the base is weak or strong. So let us find out the answer. If we want to give the answers in a few lines, we would tell that extent of dissociation of an acid depends upon the strength of a bond and the polarity of this HA bond. So please remember that the strength of an acid generally depends upon the polarity of this HA bond and strength of this HA bond. In general, when the strength of HA bond decreases, that is the energy required to break the bond decreases, HA becomes stronger acid. So the weaker is the bond between H and A, the stronger will be the acid. That is how we understand. Because H plus can be easily released, and as H plus can be easily released, this is what it happens. HA becomes the stronger acid when strength decreases. So if the bond strength between the H and A decreases, the acid becomes more and more stronger. Same way, my dear students, the polarity of this bond is also important. So polarity increases for HA bond, that is electronegativity difference between H and A increases. When the electronegativity difference between H and A increases, the polarity even increases. Why? Because there is a marked charge separation, thus the cleavage of the bond HA become easier, and that is why the acidity increases. So my dear students, here uh, it is a simple try to tell us that whenever polarity of HA bond increases, what happens? There is a marked separation between the H plus and A minus, and that is why the cleavage of HA is easy, and that is why the acidity increases. But it should be noted that acid strength in a group. Now we want to study the acid strength in a group. How do we understand the strength of an acid in a particular group? While comparing the elements in the same group, please remember the periodic table HA bond strength is more important. So when we study, my dear students, whenever we study the acid strength in a particular group, it is very important that we study about the bond strength. So the decision maker whether the acid is strong or weak is the bond strength of this HA bond. So while comparing the elements in the same group of the periodic table, HA bond strength is more important factor in determining the acidity than its polar nature. So please remember when we discuss the acidity in a group, this polarity, this bond strength between H and A is very much important, and that is what it decides whether the acid is strong or weak. As the size of A increases down the group, HA bond strength decreases. So please remember that as we go down the group, my dear students, the size of atom actually increases because new and new shells are added. So as the size of A increases down the group, HA bond strength decreases and acid strength increases. So suppose you have any particular group, and if you go and understand the bond between HA, so the size of the size of A increases down the group, and that is why the bond can be easily broken, and that is why the acid strength increases as you go down the group. So suppose, but let us understand it with example. Let us understand the same with the example. If you look into this, my dear students, we know that we have a group 17, and your group 17 is made of fluorine, chlorine, bromine and iodine. If you go down the group, my dear students, the size increases, and then you have the HF, you have HCl, you have HBr, and then you have HI. We know that hydrogen is a very small in size, and that is why the compatibility of these atoms to make bond with hydrogen actually decreases, and that is why this HA bond become more and more weaker, and as you go from HF to HI, the size of this fluorine, chlorine, bromine, iodine increases, and that is why this bond strength decreases. Bond strength decreases, and as this bond strength decreases, my dear students, the acid strength increases because the bond between this bond become weaker, and as this bond become weaker as we go down the group, the bond can be easily broken, and that is why from this H plus can be easily released, and that is why if you go down the group, the size increases. As the size increases, the bond strength decreases, and as bond become more and more weaker, H plus can be easily released, and that is why the acid strength increases. So going down the group, my dear students, acid strength increases. There is one more example which is about H2S. So if you look into the group number 16, my dear students, you have oxygen, sulfur, selenium, tellurium and polonium. So if you really move down the group, the size really increases. As the size increases, my dear students, they form the compounds with hydrogen as you have H2O, then you have H2S, then you have H2Se, then you have H2Te, then you have H2PO. These are the kinds of compound they form. We know that H2S is acidic in nature, whereas H2O is neutral. So from this itself we can say that H2S is stronger acid than H2O, because as we go down the group, the bond between the HO and H and the bond between H, S and H, this bond is weaker. So as this bond is weaker, from H2S, my dear students, we can easily release H plus and due to this release of H plus, the acid strength of H2S is more than the acid strength of water. Now, my dear students, we want to study what happens when we move in a particular group for this acid strength. So let us understand about the acid strength, my dear students, that how does the acid strength changes when we move along a period. So when we discuss the acid strength in a row, or that is what it is in the period, in a periodic table, my dear students, what happens? HA bond polarity. Now see, in a group, the acid strength is determined by the uh, bond strength, but here in a period the bond polarity become important factor. The bond polarity is the important factor to express the acid strength. Bond polarity become the deciding factor for determining the acid strength. So as electronegativity of A increases, now if you go in this direction from left to right, electronegativity increases, my dear students, because we know that in the right end of the periodic table we have non-metals, and these non-metals have higher electronegativity. So if you go from left to right in the periodic table, these non-metals are electronegative, and that is why the metallic character turns out to be non-metallic character, and that is why the electronegativity increases. So as electronegativity of A increases, the strength of acid also increases. That means if you think of the various compounds formed, you can see here, if you go from left to right, my dear students, the electronegativity increases. As the electronegativity increases, if you start looking into the, see, carbon, nitrogen, oxygen, fluorine, neon, uh, lithium, beryllium, boron. This is the second period. So in the second period, you have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Now if you think of this and make their compounds with hydrogen, you can have CH4, you can have NH3, you can have H2O, you can have HF. Now you know this H2O is actually neutral. So as H2O is neutral, these compounds are basic. We know ammonia is basic, but HF is an acid which we call it as a hydrofluoric acid. Hydrofluoric acid. So my dear students, from this we can easily come to know that this is acid, this is neutral, this is acid, this is neutral, this is base. What do we understand? The acidic character, if we study, HF has got the highest acidic character, and then if we move left side, then the acidic character decreases. But same way, if we move into the right hand side, the acidic character increases, and that is why we get this order. As you move from left to right in a period, the acidic character, my dear students, generally increases. And this is how, my dear students, we understand the various factors that affect the acid strength. These are the various important factors which really affects the acid strength, my dear students, and I hope you understood it. Now we want to study about the common ion effect and ionization of acids and bases. If you have any doubt, my dear students, you can ask me. Dear students, if you do not understand anything, you can ask me.
No, sir.
Thank you. Dear students, what can you see on your screen? Can you tell me, please?
Browser.
Can you read the common ion effect and then consider? Can you read this? Consider. Are you able to read this? Consider on your screen.
Yes,
सर
sir.
थोड़ा थोड़ा ब्लर है.
Yes, sir.
Okay. So let's move forward and understand about this. So now let us study about the common ion effect and ionization of acids and bases. Consider an example of an acetic acid dissociation equilibrium. So we have this acetic acid. This acetic acid dissociates and forms H plus and CH3COO minus. Now see, this is acetic acid. So HAC. AC is nothing but your acetate ion. So your CH3COO minus is written as AC. So now onwards, whenever you find this AC written, you need to understand it as a CH3COO minus. So this HAC ionizes into H plus and AC minus. For that we can write Ka is equal to concentration of H plus into concentration of AC minus divided by concentration of HAC. Now addition of acetate ions to an acetic acid solution decreases the H plus ion concentration. Now let us see what happens. Suppose there is an equilibrium established between the HAC, H plus and AC minus. The initial concentration for HAC was C. It was initially 0 and 0. Then you know the C alpha has been formed for H plus and AC minus, and that is why the concentration of HAC becomes C minus C alpha. Now from outside, my dear students, at the equilibrium, now from outside you add some Y mole of AC minus ions. That means from outside you simply add the AC minus ions, and as you add this AC minus ions, my dear students, let us see what happens. So when you add these AC minus ions, my dear students, what happens? You can see here that these Y moles of AC minus ions they are first added to the AC minus ions. So total moles of AC minus ion become C alpha plus Y. Now what happens, these Y moles of AC minus ions, which were extra Y mole, they actually react with H mole, H plus ions. And that is how they make the concentration of C alpha of H minus ion to C alpha minus Y. And thus the H plus ions, Y mole of H plus ions also reacts with the Y mole of AC minus ions and gives us the HAC back. Thus the concentration of HAC becomes C minus C alpha plus Y. Once again, my dear students, these AC minus ions, when they are added to this equilibrium, first of all this concentration become Y. So the concentration of AC minus become C alpha plus Y. Now this Y moles of AC minus actually reacts with H plus. So they react with Y moles of H plus. These AC minus Y moles of AC minus reacts with Y moles of H plus and gives us extra Y moles of undissociated HAC. So the concentration of HAC increases, whereas the concentration of H plus decreases, but the concentration of AC minus remains the same. This is what it happens. So now you can understand that the final concentration here in this case, we can understand it this way, that finally the concentration of HAC has been increased, but the concentration of H plus has been decreased, and the concentration of AC minus remains the same, though Y moles of AC minus has been added from the outside. Suppose from outside at equilibrium in the solution of acetic acid, if there is an equilibrium between dissociated and undissociated acetic acid and ions, now from outside if we add Y moles of AC minus ions, extra added Y moles of AC minus ions combined with Y mole of H plus ions and make Y moles of undissociated solid HAC. And thus the concentration of H plus ions are decreased by Y mole, whereas the concentration of HAC solid is increased by Y mole. Mind well that concentration of AC minus at equilibrium is C alpha, which does not change. So what happens, my dear students, that solubility of HAC, remember this, that solubility of HAC decreased because some new HAC has been formed, and as some extra or new HAC has been formed, my dear students, the solubility of HAC has been decreased. As the solubility of HAC, my dear students, has been decreased, you can say that this common ion makes the solubility of salt to be decreased. Solubility of HAC is decreased. More unsoluble, more undissociated acid is produced. Thus, concentration, when new equilibrium established, the concentration of acid is equal to C minus C alpha plus Y, whereas the concentration of H plus is equal to C alpha minus Y. Now, suppose instead of adding AC minus ions at equilibrium, from outside if we add H plus ions. So, suppose instead of adding the HAC minus ions, what happens if we add the H plus ions to this? So as this equilibrium has been established, you have this concentration C minus C alpha and C alpha, and from outside you add H plus ions which are Y moles. As from outside we add H plus ions which are Y moles, my dear students, it is easy now for you to understand, as we have discussed, the similar kind of process takes place. This extra Y moles of H plus ions makes the concentration of H plus ions at C alpha plus Y. But same time, these H plus ions, which are Y mole extra, they even combine with the Y moles of AC minus. Thus the concentration of AC minus is decreased and it becomes Ca alpha minus Y, and they both of they produce the undissolved or solid HAC. So the concentration of your HAC has been increased. Again, if you add the AC minus ions, the solubility of HAC decreases, Even if you add H plus ions, the solubility of HAC decreases and Y moles of new HAC is being produced. So that is what I want to discuss with you. If we add H plus ions, which are Y moles from outside, extra added Y mole of H plus ion disturbs the equilibrium, and to establish the equilibrium, backward reaction takes place. So newly added Y moles of H plus ion combined with Y moles of AC minus ion to give you Y moles of undissociated HAC. Thus, the solubility of HAC decreases, and concentration of various species after new equilibrium is the concentration of HAC is C minus C alpha plus Y, the concentration of H plus is C alpha, whereas the concentration of AC minus is C alpha minus Y. So, my dear students, when we add the ion which is already present into the product, what happens? The ions added decreases the solubility of the acid or decreases the solubility of the undissociated substance. Due to addition of Y mole of H plus from outside, the equilibrium is disturbed. To establish new equilibrium, the reverse reaction takes place. And as the reverse reaction takes place, this reverse reaction takes place according to the Le Chatelier's principle, because we know that according to the Le Chatelier's principles, if the concentration of product is increased, the reverse reaction takes place. The newly added Y mole of H plus combines with Y moles of AC minus, and finally when Y moles of HAC is formed, the new equilibrium is established. The concentration of H plus, when the new equilibrium is established, we would come to know that the concentration of H plus remains the same. The concentration of AC minus is decreased from C alpha to C alpha minus Y, and concentration of HAC is increased from C minus C alpha to C minus C alpha plus Y. Thus, my dear students, it must be clearly understood now up to this that solubility of HAC is decreased. The solubility of HAC is decreased when new Y mole of undissociated acid, because the new Y mole of undissociated HAC is formed. Now, when this solubility of HAC is decreased, when either if we add H plus ions, or my dear students, if we add AC minus ions. So these common ions, if we add from the outside, the solubility of the acid or solubility of HAC decreases. Now we can define the common ion effect. So this effect, what it happens, that decreases the solubility of the substance. That is what we can define it as a common ion effect. Now let us understand the definition of common ion effect. What is common ion effect? Let us look into, my dear students. The common ion effect we can define in this manner, that shift in equilibrium on adding a substance that provides more an ionic species already present at the equilibrium or present in the dissociation equilibrium, that cause decrease in the solubility of a weak salt or weak substance, is called the common ion effect. Please remember, my dear students, this is how we define the common ion effect. Let me read it once again for you. Shift in the equilibrium on adding a substance. When we add a substance which is having the common ion with the ions which are already present at equilibrium. Once again, shift in the equilibrium on adding a substance that provides more of an ionic species already present at equilibrium. So we add a species, we add an ion which is already present at equilibrium, so the equilibrium shift. What happens when the equilibrium shift? The ions we add which are already present in the dissociation equilibrium, that cause decrease in the solubility. That cause the decrease in the solubility of undissociated salt or undissociated substance, and this effect is called the common ion effect. The common ion effect is phenomena that is based on the Le Chatelier's principle. So we can explain or we can understand the common ion effect on the basis of the Le Chatelier's principle, my dear students. Now we should understand the various applications of the common ion effect. So let us learn or let us study about the various applications of the common ion effect. Using common ion effect, we can precipitate soluble salt or purify them. We can make complete precipitation of sparingly soluble salt, for gravimetric estimation and in quantitative estimation. For example, let us understand how can we do it. So first, let us discuss the first point in the purification of sodium chloride. So my dear students, using the common ion effect, we can pure the sodium chloride. From an impure sample of sodium chloride, we prepare saturated solution and then pass HCl gas through the solution. So from an impure sample of sodium chloride, we prepare saturated solution and then pass the HCl gas through this saturated solution. Due to common ion effect, Cl minus ions, we have NaCl, I think I have discussed it. So due to the common ion effect of Cl minus, pure NaCl is precipitated. Due to the effect of the common ion, due to the common ion effect, pure NaCl is precipitated and impurities like Na2SO4, that is called sodium sulfate, and magnesium sulfate do not precipitate because they do not have common ion at Cl minus. So let me explain you this once again, my dear students. We have impure sample of NaCl which contain the impurity of Na2SO4 and MgSO4. Now we have made the saturated solution of this NaCl, and from outside, my dear students, we are going to add the HCl gas. This concentration of HCl gas, we keep it more than C alpha. Please remember that the concentration of HCl gas, we keep it more than C alpha. So this, at equilibrium, we have the concentration of NaCl is C minus C alpha, and the concentration of Na plus is C alpha, and concentration of Cl minus is also C alpha. Now what happens, from the outside we add more than C alpha HCl gas. This HCl gas even produces the H plus and Cl minus ion, and the concentration of Cl minus ion is more than C alpha. So all the C alpha which are present in the Cl minus, they combine with the Na plus, and that gives us the C alpha NaCl back. Thus all the NaCl which we have dissolved, because NaCl dissociate completely. This NaCl dissociate completely. So because we have the saturated solution, all the NaCl which was possible, that has all been dissociated, and due to this, all the NaCl which was dissociated is converted back into the solid NaCl. But my dear students, Mg plus 2 and SO4 minus 2, or Na plus and SO4 minus, they do not have common Cl minus ions. So they do not precipitate back, or they do not feel common ion effect. Common ion effect. There is no common ion effect for MgSO4 and Na2SO4. There is only common ion effect for NaCl, and due to that, all the NaCl precipitates out as a solid substance, and thus we can have the impurities. MgSO4 and Na2SO4 remains into the solution. Only NaCl get precipitated, and that is how we can get the pure NaCl. So this is the first effect, or this is the first application of the common ion effect. Then my dear students, for a gravimetric estimation, what happens, sometimes we get some unknown substance and we want to know what amount of element are present into that substance. But we by some analysis, we came to know that this substance has some element X and Y. But then out of all the mass of the substance, from the from the molecular mass, what percentage of X and what percentage of Y are present into that particular substance? To know that, we do one estimation. That estimation is known as the gravimetric estimation. So common ion effect is used for almost complete precipitation of a particular ion, as it's sparingly soluble salt with very low value of solubility product for gravimetric estimation. What happens, my dear students, that this XY compound, we allow it to react with the Z, and that the compound XZ is formed. And then this XY, my dear students, we allow it to react with P, and this is how the compound PY is formed. Now we have taken suppose we have taken 100 gram of x plus xy. Here also we have taken 100 gram of xy, and then we know this mass of, suppose the mass of z is 50 gram. The mass of p is also 50 gram. Finally, what happens out of this xz and y are being produced, these py and x are being produced. Now, if this is what it is, 70 gram, if xz is 70 gram, my dear students, we can say that the x present in 100 gram is 20 gram. So this is how we come to know that out of 100 gram, there is 20 gram of X, and that is what it is, the estimation. We just take an estimation of the element that is present, and that is how, my dear students, we come to know that if there is 20 gram of X, then definitely 80 gram of Y is present. And to confirm this, we would come to know that this PY would be 130 gram produced. But it is necessary when this complete precipitation of this YZ, PY and XZ takes place. For that, there must be complete precipitation. And my dear students, as we have seen that by adding the common ion from the outside, we can have the complete precipitation of this XZ and PY. And as we can have the complete precipitation of XZ and PY, we would definitely come to know, or we can definitely estimate what amount of substance or what amount of element is present into that particular compound. Now, my dear students, we want to study about the third one, which is known as in the quantitative estimation. So, my dear students, in the first chapter, we have studied that we generally get the percentage structure. So on the basis of the percentage of carbon, nitrogen, oxygen and hydrogen given, we find out the empirical formula. That is what we have studied into the first chapter, that from given the percentage of the element, we can find out the empirical formula, and then we can find out the molecular formula. So, my dear students, when an unknown compound is being discovered, in that what amount of or what quantity of the element present, or what is the percentage of various element present into the compound, it is found out, or it is researched by the process which is known as the quantitative estimation. So in the quantitative estimation, when we are trying to find out the percentage of compound, we can precipitate silver as a silver chloride, ferric ion as its hydroxide, uh, or ferric ions as hydrated ferric oxides, and barium ion as barium sulfate for quantitative estimation. Now, to understand this point, my dear students, first we need to understand the classification of salts on the basis of their solubility. We can have the three category of salts. One salt is soluble, which is having the solubility more than 0.1 mole per liter. Some salts have solubility between 0.01 mole per liter to 0.1 mole per liter. They are known as the slightly soluble salt. But sometimes what happens, we get the sparingly soluble salts. They have their solubility less than the 0.01 mole per liter. So these are the three classes of the various salts. Now what happens, my dear students, some salts, they do not get precipitated. So when they do not get precipitated, for example, silver chloride does not get easily precipitated, and that is, this silver does not easily get precipitated because it's most of the compounds are sparingly soluble salt. So by using the chloride ions, we can completely precipitate the silver ion so that its percentage can be calculated. Same way ferric ions, which are water insoluble, or they form the sparingly soluble uh, salts, but using the hydroxide or using the oxides common ion effect, we can precipitate them as a ferric hydroxides or hydrated ferric oxides. Same way, my dear students, barium compounds which are sparingly soluble, and that is why by using the technique of common ion effect, we can precipitate them as a completely as the barium salt. And this is how, my dear students, even the sparingly soluble salt, they are precipitated completely so that the estimation or quantitative analysis of these salts can be done easily using the common ion effect. Now, my dear students, we want to solve one problem so that you can understand the concept well by looking into the practical or looking into the useful idea, and you will definitely understand it well. Let me read you the question for you. Calculate the pH of a solution. Calculate the pH of a solution of acetic acid with concentration 0.05 mole per liter, which from outside 0.05 mole of acetate ions are added if Ka is equal to 1.8 into 10 to the power minus 5 for CS3COOH, my dear students. So what happens, we have taken some acetic acid and from outside we have added the acetate ion. So how does the common ion effect takes place and how does the concentration changes, my dear students? Let us understand. So this is the given data. We have the value of Ka, we have the concentration of acetic acid, which is 0.05 mole per liter. Now extra added acetate ions, they are also 0.05 per liter. C alpha is equal to X, which is the extent of ionization. So now, my dear students, we have the solution of CS3COOH, which simply dissociate into the CS3COO minus and H plus. Now what happens, the initial concentration of CS3COOH is 0.05 mole. The concentration changes, so the concentration of reactant become less, means decreases, and concentration of product increases. The concentration of CH3COOH decreases by X, whereas the concentration of products increases by X. So at equilibrium, we will have the concentration 0.05 minus X for the CH3COOH, and for both the ions, the concentration of X and X. Now at equilibrium, my dear students, from outside we add 0.05 molar CH3COO minus ions. So you can see that we have the concentration of CH3COO minus ion, which is X. Now from outside we add 0.05 mole. So the total concentration become X plus 0.05 mole per liter. So the concentration of CH3COO minus also becomes 0.05 plus X mole per liter for CH3COOH. Now for this, my dear students, we can write the acid dissociation constant, that is CH3COO minus H plus. Now by putting all this value for CH3COO minus, we put 0.05 plus H. For H plus we write X, and for CH3COO minus, my dear students, we generally write 0.05 minus X. So by taking all this, my dear students, we know that the concentration 0.05 is far greater than the X, because our acetic acid is a weak acid and its Ka is in the order of 10 to the power minus 5. Therefore, my dear students, we will write 0.05 X is equal to either 0.05 plus X or 0.05 minus X. For both of them, my dear students, we will write simply 0.05. So here we will have the value only of 0.05. Here also we will write the value 0.05. So finally Ka would be X into 0.05 divided by 0.05. And the value of K is 1.8 into 10 to the power minus 5, that is equal to X into 0.05 divided by 0.05. This division gives us 1, and therefore X is equal to 1.8 into 10 to the power minus 5. So my dear students, this is the concentration of our H plus ions, and on the basis of that we can